Welcome to another chapter in the Burns Engineering RTDology series. I am Tony Miller. I'll be your host today. Bill Bergquist will be your presenter and expert RTDologist. Bill has a degree in mechanical engineering and serves as one of our application engineers. Bill's been with Burns Engineering for a number of years and has encountered every kind of temperature measurement issue likely to exist. All RTDology materials are developed for you to help you create a greater understanding of temperature measurement, the technology, and the best practices used for accurate temperature measurement. We won't try and sell you anything today, but should you need any temperature measurement supplies or calibration services, we encourage you to think of Burns. For more RTDology sessions, check out our YouTube channel on RTDology. Today, Bill will take a dive into some of the most common error sources in temperature measurement. We expect the presentation portion of this session to last about 30 minutes, followed by a Q&A session, in which we invite you to participate with your questions and real-world issues. We encourage you to use the chat tool located in the webinar toolkit to ask your questions. Your participation really drives this part of the session. With no further delay, here's Bill Bergquist to start our presentation.
Hello, everyone. What I wanted to do today is talk a little bit about some of the error sources with temperature measurement, with specifically RTDs. One of the most frequently asked questions I get is, well, what is the accuracy of this sensor? And that's really only about half the question. What the full question should be is, what is the accuracy of the measurement I'm trying to make? And we're going to go through and show you where a lot of these error sources come from. There are error sources associated with the temperature probe, and also the bigger source can be the actual installation. And we'll kind of step through these and talk a little bit about each one of these. And this is by no means a complete information on how to come up with an accuracy measurement. I do have some other videos that show more in detail about how you would go about calculating a measurement accuracy. And one other resource that I've really found useful is this Beginner's Guide to Uncertainty of Measurement. It's very easy to understand. It's actually the best explanation I've ever seen on this topic, and highly recommend just you can actually just Google this and get the link to it, but it's just a really good source for understanding, what is accuracy and what is uncertainty. Really recommend that. So when I start doing, a measurement error calculation, I find it helpful to have a little table, and I've come up with this list here of all the different error sources. There actually are more error sources than what I show in this table, but these are can be some of the larger contributors to that measurement error. So we go through, and there are sensor errors and there are installation errors included here. These last four are sometimes a little bit difficult to come up with because they are highly dependent on the installation, and it's just sometimes it's just an educated guess as to what the contribution of these are. So first off, we're going to look at the sensor error sources. The biggest one is the interchangeability, and this can be a little bit misunderstood. If you look at the standards, the 1137 and the 60751, both of these standards have, it's essentially a manufacturing tolerance for the temperature probe. In an ideal world, we'd be able to make the temperature probe to measure exactly 100 ohms at 0 degrees C. But of course, there are a whole bunch of different error sources that come into play in manufacturing variability. So we just have to shoot for these tolerance bands. And if we look at this one, in fact, I'm going to right here at 0 degrees C, we have the, ideally we would want that to be exactly 100 ohms, but the standards have divided this into different classes or grades of temperature probes. So like a class A or a grade A sensors has a little tighter tolerance at 0. Class B has a little wider one. And then in addition, there's a little bit of difference between the two standards. You'll see that the IEC has a little wider tolerance band as you go away from 0. And now those tolerance bands, we can either go off of a graph and get kind of a rough idea of what they are, but there are some equations that define this tolerance for different temperatures. So for example, if we were looking at this class A per the IEC standard, we take 0.15, so it's 0.15 degrees C at 0 degrees C. And to add in the difference, we would take 0.002, multiply it by the temperature in degrees C. So if we were at, like 100 degrees C, we just have that 0.002 times 100 plus 0.15. And that'll get you your interchangeability tolerance for that temperature. And here we have a little example with the grade B. And we can see that at 0 degrees C with this ASTM grade B, we're 0.25 degrees C. And just measuring at 65, the actual interchangeability is this 0.52 degrees C. And that's one thing that's really, I think, misunderstood quite a bit about these interchangeability or class and grades of PRTs. A lot of people will look at that and go, oh, it's a class A, it's 0.13 degrees C, that's perfect for what I need. But in reality, you need to look at what that interchangeability is at the temperature where the probe is going to be used. Another not very well known error source is insulation resistance. Now, the temperature probe will be affected by moisture or contamination that gets into the probe. And so any okay, little bug there. Anyway, so if we get any contamination in the probe or moisture, it's going to cause the resistance to drop in that probe. And so you're going to get a bad temperature reading. The magnitude of this error is not very large, but it is nonetheless an error source. And one of the things that it can do, in addition to just shifting that resistance down from what it actually should be, is it will make the probe not very repeatable. And that's where you'll notice it the most. And if we look at all the different temperature ranges and the potential error based on that on this table, you can see that as you go up in temperature, the insulation resistance is naturally going to drop because the capabilities of the materials, or that electrical resistance of those insulating capabilities of those materials, decrease with temperature. And you can see at maybe 300 degrees C here, we're only at 0.013. Not a very huge error, but we are at just 10 megohms. And when this 10 drops down even farther, this number, the 0.013, gets a lot bigger. So it is something to be concerned with, and insulation resistance checks should be done on the probe periodically throughout its life, just to make sure that it is staying moisture free or contamination free on the inside. So we can see moisture can get in due to a leaky seal in it. If the probe gets damaged somehow, whether the sheath might be bent or dented, if the thing went over temp at some point, that can damage the seal and allow moisture to get in and cause this insulation resistance error. Next is long-term stability. The you can call this drift. And if we look at this table here, looking down at the just the 300 degrees C usage temperature, and this is after, we typically the test is done for 1,000 hours, and you can see it. If we run the probe at 300 degrees C, it's less than 0.05 degrees C of shift. And it's a good idea to take into account a long-term stability number in your error calculation for the measurement. Again, not a very big number, but nonetheless, it still is there. And as you run the probe at a higher temperature, this error can become quite significant. Up at 500 C, we can see we're getting into that 0.35 range. So that, for some processes, can be fairly significant. Normal repeatability, it's usually expressed as a change in the ice point resistance, kind of as a percentage. This example shows 0.04 ohms. Well, pretty typical. I think what you'll find between manufacturers is it's going to be roughly in this area. Hysteresis. If you have a process that is running at a steady state, really don't need to take hysteresis into account. If you have a process where the temperature is changing widely, this can become a bit of a contributor. And what it is, as you heat the probe up and then cool it back down, it's not going to indicate the same temperature at the midpoint of that heating and cooling cycle. And that error is what we call the hysteresis error. Self-heating, since the probe is actually just a resistor made out of platinum wire, as soon as you run an electrical current through it to measure its resistance, it's going to heat up just a little bit. Same thing as what you'll see in a, like an electric space heater. You throw some power to it and those resistance coils start to get all red and they heat up. Well, at a very much less magnitude, the sensors do heat up slightly. This, again, can be a pretty small error. And if you plug in the right current to it, and it typically is 1 milliamp current is what's used in a lot of peripherals that PRTs are connected to. So they'll have, this I squared R, and we can go through this calculation and kind of figure out, in this example, it's 0.007 degrees C. So it's almost not worth plugging into the equation. To calculate this, you'd have to look at what device it's being connected to and see what those specs are for the excitation current. And then you could run through this calculation. The last one I want to talk about as far as sensor errors is the calibration. So again, in a perfect world, we'd be able to calibrate perfectly, but that's not the case. Our lab actually has an uncertainty of 0.025 degrees C for industrial grade probes. And so any number that you see from a manufacturer that says, okay, we calibrated this sensor you need to look at what their lab uncertainty is and include that in that error sources. The reason some of these errors come up is that, you know, there's the instrumentation that is involved, and then the temperature baths, whether it's an ice bath or a heated oil bath, there are temperature gradients throughout all of those, and those all contribute to that calibration error. Even some of the higher end calibration equipment is going to be affected by humidity and temperature. And I know our lab actually has some parameters that we have to meet as far as temperature and humidity so that the equipment stays within its original uncertainty estimation. So with that, I think that kind of wraps up the sensor errors, and I wanted to move into some of these real significant installation errors. And Tony, I don't know, do we have any questions that have popped up yet?
We have one here, it looks like. It's how does thermal well selection affect air?
Okay. Yeah, so we're kind of, somebody's jumping ahead a little bit, but that's good. So there's a variety of different thermal well styles, and they can have a very significant effect on accuracy of measurement. And a lot of it is due to the stem conduction. And I think maybe I'll just start going through this, and I think that will help answer the questions about you know, how selection of a thermal well can affect the measurement error.
Sure. Bill, we have another question just popped up too, if you
okay.
want to take a look at that.
Sure.
Does a PT-RTD show better performance concerning self-heating compared to NTC technology due to the lower resistance value?
Yeah, so they're looking at a you know, a thermistor, you know, a very small device, and it's you know, there's still self-heating comes into play. A lot of the thermistors have a very high resistance value, and I don't know what the exact specs are for self-heating with those. It also depends on the conductivity of the media that the sensor is in. So we did a lot of our testing in water moving at 3 feet per second. And I could imagine with a thermistor, the numbers are probably pretty similar. You know, the mass does come into play. So typically a PRT has more mass around it because it's got some, you know, usually encased in ceramic and then some kind of potting material and a stainless steel sheath around it. Whereas the thermistor can be, you know, just stuck out in an airstream and you know, and use it that way. So there is going to be some difference between the two. I just don't know the magnitude of that. So, yeah, I could do a little more research on that, maybe give you a better answer, but that's about what I have right now. So let's, if that's, Tony, if that's it, I can move ahead here.
Yeah, that's all I've got for right now.
Okay, sounds good. Stem conduction. This is one of the largest, most common error sources that come into play. And it can be a little bit difficult to make a good estimation as to what it is. Usually what I like to do is, after the probe is installed and the process is up and running, is take some insulation and wrap around external portions of the sensor, and if it's in a little pipeline or something, kind of wrap around the pipeline and see if there's any temperature change. And what that does is it isolates the temperature sensor, kind of those external portions, from the ambient conditions. And if stem conduction is coming into, or if it's happening, you'll notice a change in the indicated temperature just by adding that insulation around the outside parts of the sensor. So that can give a little bit of an idea if there is an issue there. Fortunately, there are some things that we can do to help avoid that or to minimize it. And one of the best ones is to deal with the immersion length of the sensor or sensor thermal well assembly. And what we have as an example here is, if we look at just product flowing through a pipeline, we've got our sensor installed, and we have the ambient conditions at 25 C and a couple hundred degrees C process temperature. This thermal well, connection head, and even the wires that lead down to the sensing element, they're all actually act as a thermal conductor, kind of similar to a radiator on a car. And if you don't have enough immersion length, they can actually have a little bit of a cooling effect on that sensing element. And so it's not going to be indicating the actual temperature of that fluid where it's immersed. To avoid this, we can make the thermal well smaller diameter, less mass, go with a smaller diameter probe, shorter sensitive length on the sensing element. So there's lots of things that the manufacturer can do to kind of minimize this. And then with the installation, if we get sufficient immersion length, or if we can add insulation around the outside of the temperature probe, that can help minimize this error also. If we look at a table here, and this was constructed using a tapered thermal well. This particular one was, I think it was 13.5 inches long or 12 inches long, something like that, with a 10.5 inch, or no, it looks like it was an 11 inch immersion length. So when we start out on the left side of the graph, as soon as when we get down to about, looks like about 3 to 4 inches of immersion, most of the stem conduction for this type of assembly goes away. And what I usually tell or recommend is that we go 4.5 inches as a minimum immersion to avoid stem conduction. And again, this test was done in an oil bath. The numbers are very similar for fluids that are similar, that have similar properties to water. Other fluids that, especially I've noticed some of the food beverage type products, like anything that has like a higher fat content, like maybe if you're pumping milk or cream through a pipeline, that doesn't seem to really give up its temperature quite as readily. And I've seen more stem conduction errors with products like that. This graph does apply to like most things that are kind of some of the lighter liquids like water and fuels like gasoline or diesel. So this is pretty accurate, and that 4.5 inch immersion usually works pretty well to minimize stem conduction. So we have, I'd mentioned using smaller diameter sensors. Some of the really small diameter lines where we'll have like maybe a 1/2 inch or a 1 inch diameter tube system, a probe that doesn't use a thermal well, just an 1/8 inch diameter, very tip sensitive. those we can get by with about a 1.1 inch immersion as a minimum. And that's typically put into a small tube system like that in a short outlet tee. And it can go in the outlet of the tee or the run of the tee. So if the tubing system's making a right angle bend, we could put that sensor in the run of the tee. And that works pretty well for most fluids. Time response can be another pretty significant error. When we have a process, if it's changing temperature rapidly and you need to keep track of that, or to measure that so that your controller is like putting in a right amount of heat or cooling, the temperature probe needs to be able to respond quickly to those temperature changes so that your controller doesn't get all goofed up. And if it's not responding quickly enough, let's say the temperature starts to go up and the temperature probe takes a couple minutes to respond to that, you're going to go way over temp before the controller notices that, yep, I got to turn the heating down. So that can be a real big problem, and it can be several degrees based on what the process is doing. So do need to take this into account, and there are methods that we can use to speed up a temperature probe or slow one down. Slowing it down, a good example of that is in a storage freezer where we may have people opening the door to put product in and out, and you don't want an alarm going off right away. You may want a 5-minute response time out of that probe, so you have time to put the stuff in and pull it back out. So just need to be aware of this one. It can be one of the largest ones that there is. Tony, looks like we had a couple other questions right now. I think maybe we could take one of these right now. I was just looking at this, comparing liquid to gases for stem conduction. If 4.5 inches is a good insertion for liquids, what's a good number for gases? That's a really good question. Typically for measuring specifically air temperature, you do need more immersion length. In one of the videos I've done on accuracy, I have an example in there of someone trying to measure room air temperature with probes that were sticking down from the ceiling. And they started out with a 3.5 inch, 1/4 inch diameter probe, which seemed like a good selection. And it turned out that above the ceiling, it was about 95 degrees Fahrenheit. And in the room, they had it controlled to about 70. So they were seeing some stem conduction initially. And so what we ended up doing there was taking a longer probe that they didn't want to extend down any more than about 4 inches from the ceiling to maintain headroom. So they ended up putting a 90-degree bend in a probe that was about, I don't know, I think it was probably 15 inches long. And we just went down, made a 90-degree bend in it. And that eliminated the stem conduction error. And I don't know if 15 inches was the magic number. It may have worked well with 10 or 11 inches. But the kind of the bottom line is that yes, you do need more immersion to overcome stem conduction in any kind of air, whether whatever kind of gas you may be measuring. It does make a difference. So, and there's, I don't know, it's really hard to make a good estimate of what is needed. In the room air temp thing, it was just, well, let's just get a really long probe and we know it'll work, then I just don't know exactly where that cutoff point is. So anyway, we'll move on to this lead wire error. And this comes into play when we have a 3-wire circuit in the temperature probe. There are 4-wire circuits which eliminate all of the lead resistance, but a lot of these probes are just 3-wire. And if we look at what happens there, if you can imagine having this 3-wire lead compensation work correctly, it depends on all 3 conductors having exactly the same resistance. And of course, in the real world, that's not the case. And so with the tolerances and everything on wires, we end up in this table. For example, if we look at an 18 gauge cable, and we have a sensor with a grade A interchangeability, you can run that roughly 36 feet without it kind of knocking that sensor out of its tolerance band. And these are just kind of some conservative length numbers. I know when we build a probe with a long cable on it, we'll actually balance the lead resistances in that cable. So if we have a temperature probe and it's a 3-conductor and it's got 50 feet of cable on it, we take that cable ahead of time and we will measure the resistance of each of those 3 leads, and we'll add some fixed resistance into the 2 lowest ones to bring it up to the highest one. And there's still a little bit of error in there because we can't do that adjustment exactly, but it does eliminate a lot of this type of potential error. But if you're adding your own 3-conductor lead wire onto a temperature probe, do need to be aware of this error, and the manufacturer can typically help you out and make an estimation of what that might be. I think finally here today, the instrumentation, anything you connect up to this temperature probe, whether it's a PLC or a chart recorder, data logger, transmitter, they all have error sources with them. And it's another one that needs to be accounted for in any kind of total measurement calculation. So in the last installation errors that, and these are all so specific to the installation that I'm going to recommend that you get a hold of manufacturer of the temperature probe. They can typically help you out with some estimation based on what your process type is and the fluid type, whether it's liquid or gas. They can make some really good estimations. I do this all the time for people, help them out with these kinds of calculations. We do publish a vibration spec for our temperature probes, or for many of them, based off of testing that we've done with the probe, and sometimes comparing that to what's in typical process, the vibration frequency and magnitude can be different. So, but it at least gives sort of a ballpark estimation of what it might be. So, and I think with that, we can just wrap this up. And I just kind of wanted to reiterate here that there are 2 main error sources. It's the sensor and then the installation, with the installation errors being 90% of the time the largest sources, and some of them are very challenging to figure out what they are, how to minimize them, and then deal with it and account for it in any kind of a total measurement accuracy calculation. So I think with that, if there aren't any more questions, I think we can run through some of those now. Tony, I think I'll throw that back to you.
Sure, Bill. Let's see. We have one that might have been answered already, but what is the minimum depth of an RTD probe to have no effect?
Oh, yeah. And again, that's, if it's a typical thermal well installation, 4.5 inches seems to work very well in water-like fluids. And again, to reiterate, in gases, typically need to have more than what you need to have with liquids. Now, we do have a rule of thumb for a direct immersion sensor. So that's a temperature probe that has no thermal well or anything associated with it. And it would be 10 times the probe diameter plus the sensitive length. So if we have a 1/4 inch diameter probe, so that's 0.25 times 10, that's 2.5 inches. We add the sensitive length of the probe, which is typically about 1 inch. That gives us about 3.5 inches of immersion. And that's what we would call a minimum to avoid stem conduction. And that's in liquids. So, and again, it's just a kind of a rule of thumb that covers probably 80% of the installations.
Okay, I think that's it for questions, unless anybody has anything they want to throw up here real quick. But
okay, I think I had one other one from, I think it came in earlier. Yeah, it was, it kind of relates back to this kind of rule of thumb thing, and it was a question about in pipelines,
what does pipeline skin measurement do to create air?
Oh, yeah, that one too. Okay, but this was like they wanted to know if it was go an immersion of 1/3 or 2/3 of the line size, and what is the the really truly what does it say? Truly sufficient, and does the extra length make measurement better or just create problems? And so this kind of gets to be a more in-depth question. In a pipeline, let's say it's you're running water through a pipeline. Ideally, you'd want to have a thermal well installed, 4.5 inches of minimum immersion. But if the flow rate is high enough, it can actually cause that thermal well to start to vibrate. And so you have to take that into account. And if that 4.5 inches is too long, you're going to need to shorten it up, and then you might end up with some stem conduction. So there's a bit of a balancing act there. I do have another session on thermal well selection and application, and we go into depth there about how to balance that immersion length and stem conduction, and talk about the wake frequency calculations and how to do that. And again, that's on the RTDology channel. Do we have a link to that? Yeah, right there. And so that gets to be a little more involved, but that is a good question. And I typically don't recommend going with any of those, rules of thumb for measuring flow in a pipeline. Most of the time they don't work. So it just is so highly dependent on the application and the flow rate and the characteristics of the fluid that you're trying to measure. So it's just always, it's a bit of a challenge. So anyway, that was a good one. Yep. Then the one question about the skin temperature. So if we're trying to do a surface temperature measurement on a pipe or a tube, there you have a lot of ambient air temperature conditions to take into account. And most of those are going to require some kind of insulation around them to isolate them from the ambient condition. And then you're only going to be measuring the skin temperature of the pipe and not the actual fluid. So you tend to have more conduction errors and ambient temperature effects on those types of installations. In some cases, I should say in most circumstances, that error source is fairly steady, especially if you have insulation around it and the ambient conditions are fairly steady. You can plug in an offset in your measurement system to account for it. But if it's outdoors, that can be a problem because you've got sunlight, you've got wind and rain and, wintertime, summertime, temperature variations. And that can get to be kind of a challenge for a surface temperature measurement. So is that it then, Tony?
We got one more. I think it's kind of a follow-up here. It
Okay.
says, I expect the 4.5-inch immersion is based on the thermowell type. How much would a flange thermowell affect versus a 1-inch threaded? How does a lagging affect?
Yeah. Typically, it's not going to have any effect on that number. That the 4.5 would still apply to flange thermowells or any of the threaded or socket weld or Van Stone connections. And then the part about the lagging effect, I might be a little confused on that because there's the lag in a thermowell is typically more external length of the thermowell to get it outside insulation or whatever. That doesn't really have any effect on it either. If it's a question about lagging and time response, again, the process connection type doesn't really affect the time response. It's the stem diameter and the fit up between the temperature probe and the bore in the thermal well. We try to keep that within 0.010 of an inch. And you can also speed it up with a little thermal conductive paste inside the well, just right at the very tip where the sensor is at. So I don't know, hope I answered that question. So I guess
there's another follow-up to that. Does a lag affect measurement more mass outside of the process?
Typically, I guess I don't really see much difference by, having, more mass outside of the process. Again, it's just mostly that stem diameter fit up with the temperature probe in the well. Having a big flange on it and, connection head, transmitter head, or an indicator doesn't seem to have a whole lot of effect on it. So it looks like that's it then. If anybody has any other questions, feel free to get a hold of us. There's, we're on, LinkedIn, Twitter, Facebook, whatever. And you can also send emails to info@burnsengineering.com. And I think we'll have a copy of this presentation on YouTube, probably sometime tomorrow, do you think, Tony, or is that?
Well, that might be a little ambitious. Probably a couple days.
Okay. So, I guess with that, we'll wrap this up, and thanks for joining us.